Chapter 1: Drifting into Code, the Origins and Basics of Programming. Before we talk about machines that can recognize faces, write essays, or chat with you at midnight, we start with something much simpler and, honestly, more peaceful. A computer, at its core, is not a mind. It's a machine for following instructions. The entire story of AI begins with that quiet fact. If you can describe a process clearly enough, a computer can repeat it tirelessly, perfectly, and at a scale that humans can't match. Imagine you're teaching someone a new board game, except your student is extremely literal. If you say, put the pieces where they make sense, the student just stares. But if you say, take the red piece and place it on the third square from the left, the student acts immediately. Programming is the art of giving that kind of exact instruction, step by step, until the steps add up to something useful. Early computers made this obvious in a very physical way. At first, instructions weren't friendly sentences or colorful apps. They were patterns of electricity, switches flipped on or off, holes punched in cards, wires routed in particular ways. The machine didn't understand meaning. It only recognized signals. And yet, with enough careful signals, people could make it add numbers, sort records, and calculate trajectories, tiny sparks of capability that hinted at bigger possibilities. As time moved on, humans got tired of speaking to machines in their harshest native language. So we built layers, like blankets on a cold night, between us and the raw circuitry. Those layers are programming languages. At the lowest levels, there's machine code, which is basically a long stream of tiny instructions the processor can execute directly. Above that is assembly, where those instructions get names humans can read. And above that are high-level languages, Python, JavaScript, C++, and many others, where you can express ideas in a way that resembles human thinking. This layering matters because the first example of a theme you'll see again and again in AI: abstraction. Abstraction is when you hide messy details behind a simpler interface, so you can focus on what you're trying to build. You don't need to know how a light bulb is manufactured to turn on a lamp. In the same way, you don't need to manage individual voltage changes to write a program. You just need a language that reliably translates your intention into the machine's actions. So what is a program, really? A program is a structured set of instructions that takes some input, transforms it through a sequence of steps, and produces output. That's it. Sometimes the input is a file, sometimes it's a mouse click, sometimes it's a sensor reading, and sometimes it's nothing at all, just time passing. But in every case, there's data moving through procedures. The data itself is represented in the simplest possible form: numbers. Text becomes numbers through encoding. Images become grids of numbers. Sound becomes long sequences of numbers over time. Even when a program seems to be handling something rich and human, like a poem or a photograph, under the hood, it's manipulating numerical representations. Then there's the flow of control, how the program decides which instruction to execute next. Most beginner-friendly programming can be described with just a few building blocks. You can do things in sequence: step 1, then step 2, then step 3. You can branch with decisions. If this is true, do that, otherwise do something else. And you can loop, repeat a set of steps until a condition is met. Sequence, selection, repetition. Those simple ideas power everything from a microwave timer to a spacecraft navigation system. Now let's talk about variables, because they're like little labeled jars on a shelf. A variable is a name that points to a piece of data. Instead of saying, take the number 7 and add it to the number 12, you might say, let apples be 7, let orange be 12, and let total be apples plus oranges. The labels let you think in a more human way, and they let the program remember things as it runs. Functions are the next step in making code feel less like a list of chores and more like a toolkit. A function is a named chunk of behavior, an instruction recipe you can reuse. You define it once, then call it whenever you need it. This saves effort, reduces mistakes, and most importantly, lets you build complex behavior out of simpler parts. If you've ever followed a cooking recipe that says make the sauce, and the sauce itself is another recipe, you already understand the idea. Functions are recipes inside recipes. As programs grow, humans rely on these reusable pieces to keep complexity from spilling everywhere. This is not just a convenience, it's survival. Without abstraction, Without the ability to hide detail and reuse patterns, software becomes too tangled to understand. And again, this theme will return in AI. We build systems from layers, from repeated patterns, from components that do one thing well and combine into something bigger. With that foundation, we can introduce a word that sounds fancy, but is actually very cozy: algorithm. An algorithm is simply a method, a procedure for solving a problem. If you've ever made a decision like, I'll check my keys on the table, then in my coat, then in my bag, that's an algorithm, a step-by-step strategy for finding something. In programming, algorithms often deal with organizing, searching, and transforming information. Take sorting, for example. Imagine a messy pile of books on the floor. You could sort them by title, by author, by height, by color, whatever rule you choose. The important part is that you can describe the method clearly enough that anyone could do it, including a computer. One classic method is to repeatedly find the smallest item and move it to the front. Another is to split the pile into smaller piles, sort each, then merge them. Different methods have different speeds, and computers care deeply about speed when the pile is not 10 items, but 10 million. Searching is another fundamental idea. If you want to find a name in an unsorted list, you might scan one by one. But if the list is sorted, you can do something smarter. Open the book in the middle, decide whether the name would be earlier or later, then cut the remaining search space in half, again and again. That simple trick, binary search, is a beautiful example of how structure can save time. And it hints at a deeper truth. When you organize information well, you can make better decisions faster. Now, there are two broad styles of thinking about instructions, and they're worth noticing because they echo in the world of AI. The first is imperative thinking. You tell the computer exactly how to do something. First do this, then do that, then repeat this until it's done. It's like giving turn-by-turn directions. The second is declarative thinking. You describe what you want, and some system figures out how to achieve it. I want these items sorted, rather than compare item A to item B and swap them under these conditions. SQL, the language used to query databases, is famously declarative. You ask for the result, not the method. Machine learning, in a sense, is a new kind of declarative approach. You don't write out the full step-by-step logic for recognizing a cat in a photo. Instead, you declare a goal, make correct predictions, and provide examples. The system then discovers internal rules, patterns, and representations that achieve the goal. Not perfectly, not magically, but often well enough to be transformative. And that brings us to the quiet reason this chapter matters. People sometimes talk about AI as if it floated down from the clouds in a single mysterious invention, but it didn't. AI is built on the same foundations as every other kind of software: data structures, control flow, algorithms, abstraction, and careful engineering. Even the most advanced neural network is still ultimately a program running on hardware. It executes instructions, it stores numbers, it performs operations repeatedly. The difference is not that we abandoned programming. The difference is that we started programming in a new way. Instead of handcrafting every rule, we created systems that can tune their own rules by learning from data. So as you listen, and as the story gradually shifts from code to learning, try to keep this grounding thought nearby. Nothing here is supernatural. It's human ingenuity layered on human ingenuity. Languages built on hardware, functions built on logic, models built on mathematics, and modern AI built on decades of small, steady discoveries. In the next chapter, we'll step into the earlier dreams of artificial intelligence when people tried to build minds out of logic and rules alone. And we'll see why those systems were both impressive and fragile, like a beautiful clockwork toy, precise, intricate, and easily overwhelmed by the messy, unpredictable world. But for now, just let the foundation settle. Instructions, data, loops, decisions, and methods. The simple building blocks that, when stacked high enough, start to look like intelligence from a distance. Chapter 2. From Logic to Learning, Classical AI and Its Limitations. Now that we've set down the idea of computers as instruction followers, we can wander into the first era when people tried to build something that felt like intelligence using instructions alone. In the early days of AI, a natural thought was, if intelligence is reasoning and reasoning is logic, then maybe we can create intelligence by giving a computer the right logical rules. Uh, Not learn from millions of examples, not adjust billions of parameters, but something more like a careful manual, a formal set of statements about the world, and a system that could manipulate those statements to reach conclusions. And for a while, this seemed not only possible, but inevitable. If you picture a tidy universe where facts are clear, categories are crisp, and every question has a clean answer, then rule-based AI makes perfect sense. You write down what you know. You encode it as if-then statements. If A is true, then B follows. If B and C are true, then D must be true. You chain these steps like a patient detective. This is sometimes called symbolic AI because the system works with symbols, words and tokens that stand for concepts like cat, disease, temperature, or is a kind of. In symbolic AI, you don't treat the world as a messy ocean of numbers. You treat it as a structured set of ideas that can be combined and recombined. That approach led to some early wins. Computers could solve logic puzzles, they could prove certain kinds of math theorems, they could play games with well-defined rules, they could plan routes, they could manipulate blocks in toy worlds where every object was known and every action had predictable results. And then came a particularly influential branch of this era, expert systems. An expert system is, in essence, an attempt to bottle expertise. Imagine interviewing a specialist, a doctor, a mechanic, a geologist, and asking them over and over how they make decisions. If you see this symptom, what do you suspect? If the engine makes this sound, what do you check next? The goal is to translate that human reasoning into rules so the computer can apply them consistently. The simplest form looks like this. If the patient has symptom X and symptom Y, then suspect condition Z. If the suspected condition is Z and lab result Q is positive, then confirm diagnosis Z. If the diagnosis is Z, then recommend treatment R. It sounds straightforward, and in narrow domains, with carefully curated knowledge, it can work remarkably well. Expert systems were once used for things like medical decision support, configuration of complex machinery, and troubleshooting. They could produce explanations too, which felt comforting. I concluded this because these rules fired. In a world where you want accountability, a system that can show its reasoning is attractive. But even as these systems succeeded, a quiet problem followed them everywhere. Real life is not tidy. Humans rarely reason in crisp if-then lines. Not because we're sloppy, but because the world is ambiguous. Symptoms overlap between diseases. People describe things differently. Exceptions pile up. Context changes meaning. And sometimes the right answer depends on subtle cues no one can easily articulate. This leads to a painful phenomenon called brittleness. A brittle system performs well inside its narrow comfort zone and then fails dramatically outside it. Like a beautiful porcelain cup, perfect until you drop it. A rule-based AI might handle 100 common cases, but then a slightly unusual case arrives. One missing symptom, one contradictory measurement, one new kind of phrasing, and the system either gets confused or confidently produces the wrong result. To fix brittleness, people add more rules. But adding more rules creates new problems. Rules can conflict. They can interact in unexpected ways. Updating one rule can break 10 others. The knowledge base grows into a dense forest where it's hard to know what's true, what's outdated, and what will happen when a new situation triggers a chain of reasoning. This becomes a kind of maintenance nightmare, not because the rules are incorrect, but because the complexity is combinatorial. The number of possible situations the world can present is enormous, and every additional rule is another branch in an already sprawling tree. Another challenge is something people sometimes call the knowledge acquisition bottleneck. It turns out that extracting expertise from humans is hard. Experts often can't fully explain how they know what they know. They might rely on intuition, shaped by years of experience. They might notice patterns subconsciously. When asked to explain, they give simplified stories that are useful, but incomplete. So you end up with a system that reflects how experts describe their thinking, not necessarily how they actually think. And it can feel like you're trying to build a map of a city by interviewing a few taxi drivers and writing down their favorite routes. Valuable, yes, but not the full structure of the place. Meanwhile, another strain of early AI focused on search and planning. Search is the idea that many problems can be framed as moving through a space of possibilities. In a chess game, each move creates a new board state, which leads to more moves, which leads to an enormous tree of possible futures. In route planning, you move from one location to another until you reach your destination. In puzzle solving, you apply allowed moves until the puzzle is solved. The simplest search methods are almost meditative. Try something, see if it works, and if it doesn't, back up and try another path. Depth-first search dives down one path as far as it can. Breadth-first search expands outward in layers. And more advanced methods use heuristics, educated guesses, to decide which options to explore first. Search-based AI has achieved impressive milestones, especially in games and constrained domains, but it also runs into limits. The space of possibilities can explode. Even with clever heuristics, a system can drown in options. When the world isn't neatly defined, you also face the problem of uncertainty. You may not know the outcome of an action, or you may not even know the full state of the world. In short, early AI learned a lesson that is both frustrating and deeply important. Intelligence isn't only logic, it's also pattern recognition. It's learning from experience. It's adapting when the world doesn't match your expectations. And this is where the field begins to shift, almost like a slow turning of a ship. Instead of asking, how do we write down all the rules of intelligence, researchers increasingly asked, how do we build systems that can discover rules from data? Because if you think about it, the world is constantly providing examples. People speak, and language happens. Cameras capture images, and objects appear. Sensors measure temperature, and patterns emerge. If a system could learn from those examples, it might avoid the endless labor of hand-coding every exception. This shift was not sudden, and it wasn't a rejection of everything that came before. Logic and rules still matter. Many real systems still use rule-based components because there are places where rules are reliable, ethical, and easy to verify. But the center of gravity moved toward learning. To see why, consider something deceptively simple. Recognizing a face. Try to write down explicit rules for face recognition. You might say a face has two eyes above a nose above a mouth. But then what about angle? Lighting? Glasses? Facial hair? Different expressions? Different ages? Different cameras? The rules become endless and fragile, and they don't capture what you actually mean, which is something like, I can recognize my friend across a crowded room even when the light is poor and they're smiling differently. That ability is built from experience. Your brain learns patterns over time. So a learning-based approach begins to look not just convenient, but necessary. There's also a psychological reason the shift felt compelling. Rule-based AI makes the knowledge explicit and human-readable, which sounds like a victory, until you realize that human-readable rules may not be the best shape for knowledge. The world doesn't always fit into clean sentences. Sometimes knowledge is better stored as a distributed pattern, a web of subtle associations that's hard to summarize but easy to use. Learning-based models, especially neural networks, store knowledge in that more diffuse way, not as a single line that says if X then Y, but as thousands or millions of small numerical weights that collectively shape behavior. That makes them harder to interpret, yes, but often more flexible, more robust, and more capable of handling messy reality. So the classical era leaves us with a balanced understanding. It wasn't naive, it wasn't a failure. It produced important ideas, formal reasoning, planning, search, and the practice of building systems that can explain decisions. It also revealed what happens when your system expects a perfectly described world and instead meets the world we actually live in, full of uncertainty, noise, variation, and exceptions. In a way, classical AI was like trying to build a perfect dictionary of reality before speaking a language. You can do a lot with that dictionary. You can form sentences, you can reason, but the moment you step into real conversation, you discover slang, metaphor, context, and the fact that meaning shifts with tone and situation. And now we're ready for the next step, machine learning. In the next chapter, we'll move into the gentler idea that instead of handwriting intelligence as rules, we can train it like a skill by showing examples, measuring errors, and improving through feedback. We'll see how models learn patterns, how they generalize beyond what they've seen, and why that simple training loop became the engine behind so much of modern AI. Chapter 3. a gentle introduction to machine learning. If classical AI was the era of writing down rules, machine learning is the era of letting rules emerge. Instead of telling a computer line by line how to decide something, we give it examples and a way to score its own performance. The system makes a guess, we measure how wrong that guess is, and then we adjust the system so the next guess is a little better. Not because it understands in a human sense, but because we've built a feedback loop that gradually shapes its behavior. You can think of it like teaching someone to throw a dart. You don't hand them a perfect set of equations about muscle angles and air resistance and the microscopic texture of the dartboard. You let them throw, you let them miss, you let them notice where the dart landed, and then you let them adjust. Over time, the misses become smaller, the throws become steadier, and eventually the skill looks almost effortless, though it was built from countless tiny corrections. Machine learning works the same way, except the muscles being adjusted are numbers inside a model. So let's define a few calm central terms. A model is a function, a machine that takes inputs and produces outputs. The input might be an email, the output might be spam or not spam. The input might be a photo, the output might be cat, dog, or bicycle. The input might be a list of features about a house, size, location, number of rooms. The output might be a price estimate. Learning is the process of tuning the model so its outputs become useful, and data is the experience we use to teach the model. Most of the time, we organize data into examples. Each example has an input, and sometimes it also has the correct answer, which we call a label. If we're training a model to recognize spam, the input is the email text, and the label is whether it's spam. If we're training a model to estimate house prices, the input is the house details, and the label is the sale price. When you have labels, it's called supervised learning. You're supervising the process by providing the correct answers during training. But not all learning comes with labeled answers. Sometimes we just have raw data, like millions of customer purchases or a library of photos with no tags. In that case, the model can try to find structure on its own, groups, patterns, regularities. That's unsupervised learning. And then there's a third style that feels a little like training a pet or learning a video game: reinforcement learning. Instead of labels, you have rewards. The system takes actions in an environment and receives feedback like good or bad, or a number that represents how well it did. It learns to choose actions that lead to higher reward over time. Supervised learning is learning from answers. Unsupervised learning is learning from structure. Reinforcement learning is learning from consequences. Now, to make learning possible, we need a way to represent the world in a form the model can work with. Computers, as we said earlier, deal in numbers. So machine learning often begins with turning reality into numerical descriptions, features. A feature is just a measurable property of an example. If you're predicting house prices, features might include square footage, number of bedrooms, distance to the city center, age of the building. If you're predicting whether an email is spam, features might be things like the presence of certain words, the number of links, or patterns in the sender's address. In older machine learning systems, feature engineering, hand designing good features was a major part of the craft. You could have the same algorithm, but with better features, it would suddenly perform much better. That's because the model can only learn from what you give it. If your features don't capture what matters, the model can't magically invent information that isn't there. Modern deep learning often learns features automatically from raw data, but it doesn't erase the idea. It just changes where the feature extraction happens, inside the model rather than in your handwritten preprocessing steps. Now, let's talk about training, validation, and test sets, because this is one of the most important habits in all of machine learning. And it's also one of the easiest to misunderstand. When we train a model, we show it examples and let it adjust itself to do better on those examples. But if we only measure performance on training data, we can fool ourselves. A model can become very good at the training set in a way that doesn't transfer to the real world. So we split the data. The training set is what the model learns from directly. The validation set is what we use to tune choices like model size or settings without letting the model see those examples during training. The test set is held back as a final exam, ideally untouched until the end, to estimate how well the model will do on new, unseen data. This separation helps us answer the real question, not can you remember what you studied, but can you generalize? Generalization is the heart of machine learning. A good model is not one that repeats the past perfectly. A good model is one that learns a pattern that holds beyond the data it was shown. And the great enemy of generalization is overfitting. Overfitting is when a model learns the training data too specifically. It memorizes quirks, noise, and accidental correlations. It becomes like a student who memorizes last year's exam word for word, including the typos, and then struggles when the questions are phrased differently. Underfitting is the opposite. Underfitting is when the model is too simple or trained too little and fails to capture the real pattern. It's like a student who only learned the chapter titles, not the content. Machine learning is often a dance between these two. Too much flexibility and you overfit, too little and you underfit. A lot of practical ML is about finding the sweet spot, enough capacity to learn meaningful structure, not so much that you memorize the training set. To understand how the model actually improves, we need one more gentle concept, a loss function. A loss function is a way to measure error. It takes the model's prediction and compares it to the correct answer, producing a number that says how bad the prediction was. Lower is better, higher is worse. If you're predicting house prices and the true price is 300,000, but the model predicts 360,000, the loss should reflect that miss. If you're classifying spam and the model says not spam when it actually is spam, the loss should penalize that mistake. Now we have a clear objective: adjust the model to minimize loss. That adjustment process is called optimization. You can picture optimization like walking downhill in fog. You can't see the entire landscape, but you can feel the slope under your feet. If you take small steps in the direction that reduces loss, you gradually move toward a better solution. In many ML systems, that feel the slope idea is formalized as a gradient, a signal that tells you how to change parameters to reduce loss. Even if we avoid the math for now, the emotional logic is simple. The model needs a feedback signal that says that choice made things worse, or that choice made things better. Then it can self-correct. At this point, it helps to look at a couple of simple models because they show the spirit of learning without too much machinery. Linear regression is one of the gentlest. It's used when you want to predict a number, like a price, based on features. The model assumes the output is a weighted sum of inputs. Each feature gets a weight that says how important it is. Training is basically the process of finding weights that make predictions close to the true values. Logistic regression sounds similar, but it's used for classification, predicting a category, often yes or no. It still combines features with weights, but then passes the result through a function that turns it into a probability. Instead of predicting a price, it predicts something like, there's an 87% chance this email is spam. These models are not ancient relics. They are still used because they're fast, interpretable, and often surprisingly effective. And they teach an important lesson. You don't always need a complicated system. Sometimes the world you care about is roughly linear, or close enough that a simple model works beautifully. But as tasks get richer, images, audio, language, simple models reach their limits. Real-world patterns are often non-linear. They involve interactions. A feature might matter only in combination with another feature. A word might change meaning depending on what came before it. A shape might be recognizable regardless of lighting or rotation. Capturing those patterns often requires models with more expressive power. This is where machine learning begins to lean toward deeper architectures and toward neural networks. But before we go there, there's one more practical layer to add: the messy reality of data. In textbooks, data sets are clean. In real life, data is incomplete, noisy, biased, and sometimes wrong. Sensors drift, people mislabel things, populations change over time. Systems get deployed into environments that look nothing like the training data. This is why machine learning is not just about models, it's about the entire pipeline: collecting data, cleaning it, defining labels, choosing evaluation metrics, monitoring performance, and updating systems responsibly. And it's also why we need to be careful with what accuracy means. A model can have high accuracy and still be unhelpful if the data is imbalanced. Say 99% of emails are not spam, and the model learns to always guess not spam. Technically, it would be accurate most of the time, but it would miss the point. So we often use other measures like precision and recall to understand trade-offs between different kinds of mistakes. Because in real decisions, errors have different costs. A false positive spam filter might hide an important message. A false negative might let through a scam. Machine learning is not just prediction. It's choosing what kinds of errors you can tolerate. So by the end of this chapter, you can hold machine learning in one quiet sentence. Machine learning is the process of using data and feedback to tune a model so it generalizes to new situations. It's not a mystical force, it's a structured way of improving guesses through experience. And now we're ready for the part of the story where the models become more powerful, the representations become richer, and the learning begins to feel from the outside a bit like perception. In the next chapter, we'll step into neural networks, systems built from layers of simple units that together can learn complex patterns. We'll explore how they transform inputs into internal representations, how they learn through many small adjustments, and why deep learning became the engine that carried AI into its modern era. Chapter 4: Neural Networks from Neurons to Deep Learning. If machine learning is the idea of improving by feedback, neural networks are one of the most successful ways we've ever built a model that can absorb that feedback and turn it into skill. They're called neural not because they are literal brains, but because the original inspiration came from a simplified picture of neurons. Many small units, each doing something simple, so connected into a larger system that can do something complex. It's a metaphor, useful, imperfect, and a little poetic. The important part is not biology. The important part is composition. Small computations stacked together to create powerful transformations. So let's begin with a single artificial neuron, sometimes called a unit. A neuron receives inputs, numbers, and combines them. Each input has a weight, which is another number that says how strongly that input should matter. The neuron multiplies inputs by weights, adds them up, adds a bias term, a kind of adjustable baseline, and then passes the result through an activation function. That activation function is crucial. Without it, the neuron would be just a linear calculator, and stacking linear calculators gives you another linear calculator. Useful but limited. The activation introduces nonlinearity, which is a fancy way of saying it allows the model to bend, curve, and shape its behavior to match the world. If that sounds abstract, picture it like dimmer switches versus on-off switches. Linear functions are like dimmers, smooth, proportional, predictable. Nonlinear activations are like adding quirks and thresholds. I'll respond strongly only after a certain point, or I'll compress big numbers so they don't explode. Those quirks let the network present complicated patterns. Now, one neuron is not very impressive, but neurons don't work alone. We arrange them in layers. A layer is a group of neurons that all take the same input and produce a set of outputs. Then another layer takes those outputs as its inputs, and so on. The input layer receives raw features. Hidden layers transform them into internal representations. The output layer produces predictions. This layering is another echo of abstraction. Early layers might learn simple patterns, and later layers learn patterns built from patterns. In image models, early layers often learn edges and textures, later layers learn shapes and parts, and later still they learn object-like concepts. In language models, early layers might learn short-range relationships between tokens, while deeper layers capture longer-range structure. When a neural network produces an output from an input, we call it a forward pass. It's the network thinking in the most mechanical sense, numbers flowing forward through layers. But the real magic, meaning the real engineering triumph, is how the network learns. Learning means adjusting the weights and biases so that the forward pass becomes more accurate over time. To do that, we need a loss function, just like in the previous chapter, a way to score how wrong the network's output is. Then we need a way to answer a delicate question: which weights are responsible for the error and by how much? That's where backpropagation comes in. Backpropagation is not a mysterious new kind of intelligence. It's bookkeeping for blame. When the network makes a prediction and the loss tells us it was wrong, Backpropagation computes how much each weight contributed to that wrongness, not in a moral way, just in a mathematical way. It traces the influence of each weight on the final output, layer by layer, from the end back toward the beginning. If the network is a factory assembly line, backprop is the quality inspector walking backward along the line, noting which station settings nudge the product out of spec and how to nudge them back. The output of this blame bookkeeping is a set of gradients. A gradient is a direction. It tells you how to change a parameter to increase or decrease the loss. In training, we want to decrease the loss, so we move parameters in the opposite direction of the gradient. That movement is done by an optimizer. The simplest optimizer is gradient descent. Take the gradient, multiply by a learning rate, a step size, and subtract it from the weights. Repeat this many times over many examples, and the network gradually improves. The learning rate is like how cautiously you walk downhill in that foggy landscape. Too large and you overshoot, bouncing around, never settling. Too small and you make progress so slowly that you might not get anywhere practical. Much of neural network training is in spirit about making steady progress without losing stability, because stability is the quiet challenge of deep learning. Neural networks, especially deep ones, can be temperamental. Early researchers ran into problems like vanishing gradients, where the learning signal gets weaker as it travels backward through many layers, so the early layers barely learn. Sometimes the opposite happens, exploding gradients, where values grow wildly and training becomes chaotic. A lot of the history of deep learning is the history of practical fixes, better activation functions, better initialization methods, better optimizers, normalization techniques, and architectural designs that help gradients flow. One famous change was the move away from older activations like sigmoid in many deep networks and toward functions like ReLU, which is simple. It outputs 0 for negative inputs and passes positive inputs through. It sounds almost too basic, but it helped training enormously by keeping gradients healthier in many settings. Chapter 5. Language, Sequences, and the Rise of Transformers. Language is one of those everyday miracles we hardly notice. You hear a sentence once in a noisy room, and your mind calmly reconstructs meaning. You understand references, jokes, implications, and tone. You can tell when someone is being sincere, sarcastic, uncertain, or careful, and you do it with an ease that makes it feel like language is simple. For a computer, language is not simple at all. Not because words are mysterious, but because words are slippery. The same word can mean different things in different contexts. Bank can hold money or border a river. Right can mean correct or a direction or a legal entitlement. Even small changes in order can flip meaning. The dog chased the cat is not the same as the cat chased the dog, even though the words are almost identical. So if we want machines to work with language, we need a way to represent words and their relationships without handwriting a rule for every possible sentence. The earliest and simplest approach is to treat words like tokens in a bag. You count them. You notice which words appear and how often. This can work for some tasks, like basic topic detection, because certain words strongly hint at certain topics. But it throws away the sequence. It doesn't capture grammar or negation or the way meaning depends on what came before. And sequence is everything in language. A natural next step is to process text in order, like a river, one token after another. That's where sequence models come in. But before any model can process text, we have to solve a basic problem. Computers want numbers. Words are not numbers, so we translate. At first, people used one-hot encodings, a huge list of possible words, where each word is represented as a vector of mostly zeros, with a single one in the position corresponding to that word. It's simple, but it treats every word as equally unrelated to every other. Cat and kitten are just two different positions. There's no built-in sense that they're similar. Then came a more graceful representation, embeddings. An embedding is a learned mapping from words or tokens into a vector space, where similar words tend to have vectors that are close together. In that space, cat might be near kitten, dog, and pet, and farther from volcano or accounting. This doesn't mean the model understands cats the way you do, but it does mean the model has a numerical geometry that captures useful relationships. Embeddings are like giving words coordinates in a meaning-shaped landscape. Once you have embeddings, you can feed them into a sequence model. Recurrent neural networks, the RNNs we mentioned earlier, were designed for exactly this. They read a sequence one step at a time. At each step, they take the current token's embedding and combine it with a hidden state, a compact summary of what has been seen so far. The hidden state is then updated and carried forward. If you imagine the model reading a sentence, the hidden state is like a little notebook it keeps in its pocket. It can't write everything down, but it can keep a running summary. What topic we're on, who she might refer to, whether we're inside a quote, whether the sentence has already been negated. In practice, early RNNs had trouble keeping information over long distances. The further back something was, the more it faded. This matters because language often depends on distant context. Pronouns refer back. Clauses open and close. Meaning accumulates over time. To address this, LSTMs and GRUs introduced gates, mechanisms to decide what to keep, what to forget, and what to update. They improved long-range memory and made sequence learning more reliable. And for a time, RNNs and LSTMs were the main way neural networks handled language. But they had limitations that became more obvious as ambitions grew. One issue is that they process tokens sequentially. The model reads one token, updates its state, then reads the next. This is natural, but it's slow to train at scale because the computation doesn't parallelize easily. Modern AI thrives on parallelism, doing many operations at once on powerful hardware. Another issue is that even with LSTMs, capturing very long-range dependencies is difficult. The notebook in the pocket can only hold so much, and the signal of what matters can weaken as sequences grow longer. Meanwhile, a different idea was emerging, an idea that would change the shape of modern AI: attention. Attention, in this context, is not about emotion or consciousness, it's about selective focus. When you read a sentence like, "The book that the teacher who arrived late mentioned was missing," your brain doesn't treat every word equally at every moment. You focus on relevant parts to resolve meaning. Attention mechanisms let a model do something similar. When processing one token, it can look back at other tokens and decide which ones are most relevant. Instead of squeezing the whole past into a single hidden state, attention provides a way to consult the past directly. If RNNs are like reading with a single running summary, attention is like reading with the ability to glance back at the page whenever you need. You don't have to remember everything perfectly. You can recheck the parts that matter. This idea becomes especially powerful when you let every token attend to every other token in the sequence. That's self-attention. Self-attention builds relationships between tokens, which words modify which nouns pair with which verbs, which earlier phrase a pronoun refers to, which details matter for the current prediction. And then came the transformer, introduced in the famous work often summarized as "attention is all you need." The transformer architecture replaced recurrence with layers built largely from self-attention and simple feed-forward transformations. This changed everything for a few key reasons. First, transformers parallelize well. Instead of processing tokens one at a time, a transformer can process an entire sequence in a more parallel fashion during training. This makes it far more compatible with modern hardware and large-scale datasets. Second, self-attention handles long-range dependencies more naturally. Any token can directly attend to any other token in the sequence. There's no need for information to be carried step by step through a long chain where it might fade. Third, transformers scale. When you make them bigger, more layers, wider layers, more data, they tend to improve in a surprisingly smooth and predictable way. Now, let's slowly unpack the transformer's key ideas without getting lost in technical fog. A transformer takes a sequence of tokens and turns them into embeddings. But unlike a simple bag of words model, it needs to know the order of tokens. If we shuffle a sentence, it changes meaning. So transformers add positional information, often via positional encodings, which give the model a sense of where each token sits in the sequence. Then the model applies multi-head self-attention. The multi-head part means the model doesn't just have one way of looking at relationships, it has multiple attention heads, each able to focus on different kinds of patterns. One head might learn to track direct grammatical links, another might learn to connect pronouns to their antecedents, another might learn to focus on punctuation or formatting cues. They're not hand-assigned, They emerge during training. After attention, the model applies a feed-forward network to each position, transforming the representation further, and this repeats through many layers. Throughout the architecture, there are skip connections, paths that let information flow around transformations, and normalization steps that help training remain stable. These are part of the deep learning toolkit that makes very deep networks trainable. Transformers come in a couple of common shapes. An encoder-decoder transformer has two parts. The encoder reads an input sequence and produces a rich representation of it. Decoder generates an output sequence, attending both to its own previous output tokens and to the encoder's representation. This is a natural fit for translation. The encoder reads the source language, the decoder writes the target language. A decoder-only transformer, by contrast, is built to generate text by predicting the next token given previous tokens. It uses masked self-attention, meaning it can't peek at future tokens during training. It learns to continue sequences, to complete prompts, to generate coherent passages. Modern large language models are often decoder-only transformers because next token prediction scales well and can absorb enormous amounts of text. This brings us to a subtle but important point. Why does predicting the next token lead to so many abilities? On the surface, next token prediction sounds narrow, almost silly, like teaching someone to speak by making them guess the next word over and over. But language contains compressed knowledge about the world. Text encodes facts, instructions, stories, arguments, code, mathematics, and the patterns of how humans explain things. To predict what comes next across a huge and varied dataset, a model has to internalize many regularities: grammar, style, common sense patterns, domain-specific conventions, and even fragments of reasoning strategies. It doesn't become a perfect thinker. It doesn't become a reliable fact database, but it becomes a powerful pattern model of language and the ideas that language carries. Transformers made this feasible at scale because they could train efficiently on modern compute, and because their architecture was flexible enough to absorb and express complex patterns. There is, however, a cost. Self-attention can be expensive for very long sequences because naively it considers relationships between every pair of tokens. That's one reason you hear so much about context length and memory efficiency. The industry has developed many tricks and variants to handle longer contexts, but the core idea remains. Transformers trade some computational cost for expressive power and parallel training. So by the end of this chapter, you can hold the rise of transformers in a calm storyline. We started by trying to force language into rigid rules, which didn't scale. We moved to machine learning and neural networks, which learn from data. We built sequence models like RNNs and LSTMs to handle order and context. We discovered attention as a better way to manage long-range relationships. And transformers combined attention with deep learning engineering to create models that train efficiently, scale smoothly, and handle language with impressive flexibility. In the next chapter, we'll step into what happens when you take transformers and scale them up into large language models. We'll talk about tokens and parameters, datasets and compute, pre-training and evaluation, how these models are actually trained, and why the training process shapes both their strengths and their limitations. Chapter 6. Training large language models. If transformers are the shape of the engine, training is the long, steady journey that turns a silent engine into something that can actually carry you somewhere. A large language model begins life as a collection of numbers, parameters, initialized in a way that is, for all practical purposes, random. At that stage, it doesn't know anything. If you asked it to continue a sentence, it would produce nonsense because it has no patterns to draw from yet. Training is how patterns get carved into those numbers. The core idea is surprisingly simple. Show the model a piece of text and ask it to predict what comes next. Then compare its prediction to what actually came next. Measure the error. Adjust the parameters so the next prediction is slightly better. Repeat millions or billions of times. This is next token prediction. It is the heartbeat of many modern language models. To make this work, we need a unit of text small enough to handle consistently. That's where tokens come in. A token is not exactly a word. Sometimes it is a whole word, sometimes part of a word, sometimes punctuation, sometimes a frequent fragment like ing or tn, sometimes a space plus a word. Tokenization is the process of turning text into a sequence of these pieces, so the model can process language as a stream of discrete units. Once text is tokenized, each token becomes a number, an ID, and that ID is mapped into an embedding vector. From there, the transformer layers do their work, and the model outputs a probability distribution over possible next tokens. Training nudges the model so the probability mass shifts toward the correct continuation more often. If you want a calm intuition, the model is learning the habit of being unsurprised by real text. It adjusts itself until the continuations it expects look more like the continuations humans actually write. But training a large language model isn't just press start and wait. It's a massive engineering project, and it has a few pillars: data, compute, optimization, and evaluation. Let's start with data. When people say trained on the internet, that can sound vague, like the model inhaled the entire web in one breath. In reality, training data is assembled from many sources: web pages, books, academic papers, code repositories, encyclopedic text, forums, and more. Then it's filtered. Duplicates are reduced. Some content is removed for quality, safety, and legality. Some content is downweighted or excluded. The details vary by project, but the basic point is the dataset is curated even if imperfectly. And dataset choices matter. They shape the model's voice, its strengths, its blind spots, and its biases. A model trained heavily on code tends to be better at code. A model trained heavily on scientific text tends to sound more formal and technical. A model trained heavily on casual conversation will mirror casual language patterns. Now compute. Training is expensive because the model must process enormous amounts of text, and every step involves large matrix multiplications, operations that GPUs and TPUs are very good at, but still not infinitely fast. This is why large training runs involve clusters of accelerators working together, often with elaborate systems to split the model and the data across many devices. And then there's the question people always ask: what makes a model large? Most commonly, it refers to parameter count, the number of adjustable weights in the network. More parameters generally mean more capacity to store patterns. But parameters aren't the whole story. The amount and quality of data matters. The training duration matters. The architecture matters. The optimization matters. In practice, performance comes from the combination. There's a quiet principle that emerged over years of experiments: scaling laws. Roughly speaking, as you increase compute, data, and model size in a balanced way, performance tends to improve predictably. Not forever, not without caveats, but enough to guide how people plan training runs. This predictability is part of why the field accelerated. If bigger reliably tends to be better when done carefully, then scaling becomes a straightforward, if costly, path forward. Now, optimization at scale. Training is not just about learning, it's about learning stably. You can't always feed the model one example at a time. Instead, you use batches, many examples processed together, to make better use of hardware. But very large batches can change the feel of training, sometimes harming generalization. So practitioners tune batch size, learning rate, and other settings to find a stable path. They also use techniques like learning rate schedules, where the learning rate changes over time, often starting larger and then gradually shrinking. It's like learning a new skill. Early on, you make big corrections. Later, you refine. And because training runs are so long, models are saved as checkpoints along the way. If something fails, hardware issues, instability, a power event, you don't want to lose weeks of progress. Checkpoints also allow evaluation at different stages to understand how capabilities emerge, which brings us to evaluation. How do you know whether a model is good? One way is perplexity, a measure related to how well it predicts text. Lower perplexity generally means better next token prediction. But people care about tasks. Can it answer questions, write coherent summaries, translate, solve problems, write code? So models are tested on benchmarks, standardized data sets meant to measure certain abilities. Some benchmarks test knowledge recall. Some test reasoning. Some test math. Some test coding. Some test reading comprehension. But evaluation is tricky. Benchmarks can be gamed unintentionally. They can leak into training data. They can become outdated. They can reward superficial pattern matching. So serious evaluation often combines many tests with human judgment and careful data handling. And even with good evaluation, there's a sobering truth. A language model is not a database of guaranteed facts. It's a probability machine trained to produce likely continuations. It can sound certain while being wrong. It can blend true and false. Its confidence is not a reliable indicator of correctness. So training gives us a powerful engine, but not automatically a safe or helpful one. A pre-trained model is like a brilliant autocomplete that has absorbed a vast library. It can imitate styles, it can produce plausible text, it can continue almost any prompt. But it may also be inconsistent, overly eager, or misaligned with what a user actually wants. And that's where the next chapter begins, turning raw language models into helpful assistants, systems that don't merely continue text, but try to cooperate with people. Chapter 7. From raw models to helpful assistants. Imagine you build an extremely talented musician who can play almost any style at any tempo in any mood, but you never teach them the difference between a rehearsal, a concert, and a lullaby. They might perform brilliantly, but not always appropriately. A pre-trained language model is a bit like that. It has learned a great deal about patterns in text, but it hasn't necessarily learned how to be helpful, honest, careful, or aligned with human intent. It hasn't been trained specifically to follow instructions the way people expect in a conversation. So the next phase in the story is refinement. One common approach is fine-tuning, taking a pre-trained model and continuing training on a more specific data set. If you want a model that excels at legal writing, you might fine-tune it on legal documents. If you want it to be better at customer support, you fine-tune on support conversations. Fine-tuning nudges the model toward a particular domain or behavior. Another important step is instruction tuning. Instruction tuning is training on examples where the input is an instruction and the output is an appropriate response. Explain photosynthesis. Summarize this text. Write a polite email declining a meeting. The model learns that prompts are not just text to continue, they are requests to satisfy. This changes the interaction style dramatically. It's part of why modern chat models feel cooperative rather than purely generative. Then comes a deeper form of shaping behavior, learning from human feedback. One popular family of methods is often described as reinforcement learning from human feedback, or RLHF. The idea is simple to say. Humans compare model responses and indicate which ones are better, more helpful, more accurate, more safe, more aligned with guidelines. From these comparisons, you train a reward model that can predict which responses humans would prefer. Then you train the language model to maximize that reward. In calmer terms, you're teaching the model a taste for better answers. This doesn't make it perfect. It doesn't remove hallucinations entirely, but it often improves the model's willingness to follow instructions, refuse harmful requests, and stay on track. Alongside this, there are safety layers. Some are in the model itself, learned behavior. Some are outside the model, filters and classifiers that detect unsafe content. Some are policy-driven constraints. Modern systems often combine all three. There's also the growing role of tools. A language model on its own is limited to what it can infer from its training and its prompt. But you can connect it to tools, a calculator, a database, a search system, a code interpreter, a calendar, a knowledge base. When a model uses tools, it can stop guessing and start checking. It can retrieve information instead of inventing it. It can compute precisely instead of approximating. One of the most important tool patterns is retrieval augmented generation, RAG. Here, when you ask a question, the system retrieves relevant documents from a trusted source and then asks the model to answer using those documents. This can reduce hallucinations and keep answers grounded. At that point, the model becomes less like a solitary writer and more like a coordinator, reading, selecting evidence, summarizing, and composing. This naturally leads to agents. An agent is a system that can plan and take steps. It might break a goal into subtasks. First find information, then compare options, then draft an output, then revise. It might call tools along the way. It might check its own work, not always perfectly, but in a structured way that resembles workflow. When people say AI can do tasks, they often mean a combination of a language model plus tools, plus a loop that lets it act and verify. Still, even at this stage, it's important to stay grounded. These systems do not have desires or understanding in the human sense. They have objectives shaped by training and feedback. They produce text that matches learned patterns, and they can be guided by reward signals and constraints. They can be very useful and also very fallible. So the question becomes practical. How do we build with them responsibly? How do we use their strengths without being trapped by their weaknesses? That's what we'll explore next. The real world patterns people use to make LLMs useful: summarization, coding help, search, RAG, workflows, and the design choices that separate a delightful assistant from a confusing one. Chapter 8: Building with LLMs, Applications and Design Patterns. Once you have a capable assistant model, you step into a different kind of craft. It's no longer only train a model, it becomes design a system. And in system design, the most important question is, what do you want the model to do reliably in the world you actually have? One of the simplest and most common applications is conversational help, answering questions, explaining concepts, brainstorming ideas, drafting messages. This works well because language models are naturally fluent. They are good at taking an intent expressed in words and producing a structured response in words. But even here, the design matters. A good assistant needs context: what the user wants, what constraints they have, what tone is appropriate, what format is expected. Sometimes that context is provided in the prompt. Sometimes it's stored as conversation history. Sometimes it's pulled from a profile or a document. The model's output quality depends strongly on how well you frame the task. Another major use is summarization and transformation. Summarizing long documents, extracting key points, rewriting text for tone, translating between languages, converting bullet points into prose, turning prose into bullet points. These are tasks where the model's natural strength, mapping one piece of text into another, shines. Then there's code. LLMs can be surprisingly helpful with programming because code is a language with strong patterns. They can generate boilerplate, explain errors, refactor, write tests, and suggest approaches. They are not always correct, but they can accelerate a developer's thinking, especially when paired with execution and verification. A crucial design principle here is don't trust, verify. If the model writes code, run it. If it makes a factual claim, check it. If it summarizes a contract, compare it against the source. LLMs are excellent at producing plausible outputs. Your system should be excellent at checking plausibility against reality. This is why retrieval and tool use are so central. In retrieval-augmented systems, the workflow often looks like a calm three-step: retrieve, read, respond. First, retrieve relevant chunks from a trusted corpus. Second, feed those chunks to the model with clear instructions. Use only these sources, cite them, don't invent. Third, generate an answer. Even then, you need guardrails. You may need to detect when retrieval failed, when the system didn't find anything relevant, and ask the user for clarification rather than guessing. You may also need to manage context length. Models can only see a limited amount of text at once, so you must choose what to include: the most relevant sections, the most recent conversation, the most important constraints. This is a quiet art. Choosing the right context is often more important than choosing a fancier model. Another design pattern is structured output. Instead of asking the model to respond freely, you ask it to produce a specific format: JSON fields, a table, a checklist, a set of steps, a template. This reduces ambiguity and makes the output easier for downstream systems to parse and validate. In other words, you turn a conversation into a contract. Respond in this structure so I can use it safely. Then there's the human-in-the-loop pattern, which is especially important for high-stakes domains. Here the model drafts and a human reviews, or the model proposes options and a human chooses, or the model flags uncertainty and asks for confirmation. The goal is not to remove humans, but to make human effort more focused: less time spent on first drafts and more time spent on judgment. And finally, there's the simple pattern of iteration: draft, critique, revise. A user can ask the model to produce something, then ask it to improve it, then ask it to check for errors, then ask it to adapt to a different audience. LLMs are good at revision because revision is also language transformation. But every pattern has limits. If the model lacks information, it may hallucinate. If it is given conflicting instructions, it may behave inconsistently. If it is asked to do something that requires precise, grounded knowledge without retrieval, it may sound persuasive rather than be correct. If it is deployed without monitoring, It may drift as user behavior changes. So building with LLMs is about designing for reality, grounding, verification, structure, fallback behavior, and careful framing. And as systems become widespread, another layer becomes unavoidable, the social layer, the impacts, the risks, the responsibilities. That's our next chapter, the limits, ethics, and practical realities of AI, spoken gently, but without pretending the issues aren't real. Chapter 9, Limits, Ethics, and Practical Realities of AI. It's tempting to treat AI progress like a steady climb. Smarter models, better tools, more helpful systems, and then, somewhere out there, an almost magical future. But the real story is more complicated and more human. Large language models can be deeply useful and also deeply imperfect. Their limitations aren't small footnotes, they are central features of what these systems are. One limitation you hear about often is hallucination. The model generates information that sounds plausible, but is incorrect or fabricated. This happens because the model's training objective is to produce likely text, not guaranteed truth. If a prompt strongly suggests that an answer exists, the model may produce something that fits the shape of an answer, even if it doesn't have reliable grounding. A model can be fluent and wrong at the same time. This is why careful systems use retrieval, citations, tool calls, and verification, ways of tying the model's words back to evidence. Another limitation is bias. If a model is trained on human text, it absorbs human patterns, good and bad. It may reflect stereotypes present in data. It may treat some dialects or cultures as more standard than others. It may underrepresent groups that appear less in the training corpus. Bias can appear in subtle ways: tone, assumptions, what the model considers normal, what it considers expert, what it considers safe. Reducing bias is not a one-time fix in a process involving data curation, evaluation, feedback, and transparent goals. Then there's privacy. Training data may contain sensitive information. Even if datasets are filtered, the scale is huge and mistakes can happen. Additionally, deployed systems can be used in ways that leak sensitive data. Users may paste private documents, confidential code, personal messages. Responsible systems include controls, data handling policies, retention limits, access boundaries, and user education. Security is another layer. Models can be manipulated through prompts. They can be coaxed into revealing information they shouldn't or into producing harmful content. They can be used to write phishing messages, generate malware snippets, or automate scams. Safety measures help, but they are not absolute. Security becomes a system-wide effort. Model behavior, filtering, rate limits, user authentication, monitoring, and incident response. There is also the question of reliability. In many domains, medicine, law, finance, being usually right is not enough. You need to know when you might be wrong. Uncertainty estimation, citations, provenance, and human oversight become essential. And finally, there are the broader impacts, economic and environmental. Training and serving large models consumes energy. It requires hardware supply chains. It concentrates capability in organizations that can afford compute. Meanwhile, AI tools can change labor markets, shifting what skills are valuable, altering workflows, and sometimes displacing certain tasks. At the same time, AI can increase productivity, accessibility, and creativity. It can help people write, learn, code, translate, and communicate. It can support research and accelerate discovery. The ethical reality is not a single conclusion. It's a set of trade-offs that society must choose deliberately rather than sleepwalking into. That means governance matters. Clear standards, careful regulation where appropriate, and transparency about what systems can and can't do. It also means everyday responsibility matters. Developers and users choosing verification, respecting privacy, and treating AI output as assistance, not authority. So the gentle takeaway is this: AI is powerful, but it is not automatically good. It becomes beneficial when it's built and used with care. And with that grounded view, we can look forward, not with hype and not with fear, but with calm curiosity toward where this technology may go next. Chapter 10, The Road Ahead, Future Directions in AI and LLMs. If you zoom out far enough, the story of AI development is a story of compression. We compress experience into models. We compress language into tokens. We compress patterns into parameters. We compress vast libraries into systems that can respond in a moment. The next chapter of that story is likely to be shaped by three themes: multimodality, efficiency, and integration. Multimodality means models that work across more than text, images, audio, video, sensor data, and mixtures of all of them. Humans don't learn the world through text alone. We learn through sight, sound, motion, and interaction. When models can connect those streams, they can become more grounded and more useful, describing an image accurately, interpreting a chart, understanding a spoken question, helping with a physical task, or reasoning across different kinds of evidence. Efficiency is the second theme. For a while, the easiest path forward was scale. Bigger models, bigger data, bigger compute. But the world also wants smaller, faster, cheaper models that run on everyday devices, protect privacy, and reduce energy use. That drives work on compression, distillation, quantization, better architectures, and smarter training methods, ways to get more capability per unit of compute. Integration is the third theme. The most useful AI systems are not isolated chatbots. They are woven into workflows, editors, IDEs, search engines, customer support platforms, research tools, and personal knowledge systems. They retrieve information, cite sources, call tools, schedule actions, update documents, and collaborate with humans. In that world, intelligence often looks less like one model being brilliant in isolation and more like a system being reliable, good at asking clarifying questions, good at checking work, good at respecting constraints, good at knowing when to defer. We may also see progress in how models reason, not necessarily by becoming mystical thinkers, but by being trained and scaffolded to plan, verify, and reflect. Some of this will come from better data sets, some from better tool use, some from architectures that handle longer contexts and more structured memory, and some from careful training that rewards consistency and truthfulness, not just eloquence. At the same time, the limits will remain important. No matter how fluent a model becomes, it will still be a system shaped by its training objective and its data. It will still need grounding, it will still need evaluation, it will still need oversight in high-stakes settings. The future will not remove responsibility, it will increase it. So as we come to the end of this long, slow journey, from basic code to rules and logic, to learning from data to neural networks to attention and transformers, to large language models and the systems built around them, you can hold one simple, comforting idea. AI development is not one magical leap. It is many small steps layered patiently over time, and that means the story is still being written by researchers, engineers, policymakers, artists, educators, and everyday users choosing how to use these tools. If you've stayed awake, I hope the path feels clearer now. How instructions became programs, how programs became learning systems, and how learning systems became language models that can speak in a way that feels strangely familiar. And if you've drifted off at any point, that's perfectly fine too. The world of AI will still be here tomorrow, built from calm mathematics, careful engineering, and the endlessly human desire to understand, to build, and to make meaning from patterns.